So I'm just being lazy. All right, good morning, everyone. So just a reminder we talked about yesterday. So at the end, we talked a little bit briefly about plane waves, or plane mirrors, but we talked about basically everything we need to know. So again, we said plane mirror is where we have a radius of curvature equal to infinity. So meaning it's just a plane. In this case, we're going to create a image from there, from this particular object. So this is my object, which has a height of h, and this is some object distance away from the mirror. And then by ray tracing, we found was that the image in this case, which has a height of h prime and a distance of s prime away from the mirror itself, is formed. And what we noted was all the angles and everything were the same, so the triangles were the same, so therefore all these distances are the same. So all this then says is that the image distance then is equal to negative of the object distance, where the negative sign just means it's on the backside then of the mirror. And then the height stays exactly the same. So that's our plane mirrors. So, nice and boring. So having said that, we'll start off with a nice group of assignments. So this says that we want to know how far from you is the third image of yourself in the mirror in front of you. Comparatively, is the image facing you or is it facing away from you? So have you ever gone to a grocery store? I used to do this as a kid because it was kind of fun, where they had the cold cuts and everything. You could stick your head in. They usually had one mirror here and one mirror here. If you looked in one direction, you would basically see an infinite number of copies of yourself in both directions. Okay? That's what's happening here. So basically what's going to happen then is like each one of these mirrors then is going to create an image. Okay. But the image which is created by that mirror will also then create an image in the other mirror. So what do I mean by that? So let's kind of make our drawing here. So let me bring this up. So here's my example. Turns out I drew my head in the wrong direction. I'm actually looking this way. I'm in the wrong spot. So in this case, I'm looking in this direction. Okay. So basically what's going to happen is what? From this mirror over here, the one in front of me, so this is the front mirror, and this is the back mirror. So what's going to happen in this case then is I'm going to create an image here by looking at myself from here. So this image is going to be looking back at me. But simultaneously, from this mirror back here, the back of my head is going to create an image on this side. So I'm also going to simultaneously create an image over here. So this is the image of me here, where this one then is going to be looking away, which means I'm going to see the backside of my head if I was looking backwards. Right? But this image over here will then create an image over here. So I'm going to simultaneously use this one to create an image over here, which then would be looking away from me. But then this image here is going to create an image over here, which would be looking towards me. And then simultaneously, this image here would also create an image on this side. Okay? And this is just going to keep happening indefinitely. So your job then is to figure out what is the distance that this third image would be over here, which we've now just established it's actually going to be looking at me because it's created from this image over here. So that's going to be actually looking at me. So now we know it's looking towards us. Well, we want to figure out that how far away is this actual image created. Okay. Now, again, distances here are nice and easy, which means that this distance here is x2, then this distance is also x2. Which means the total distance away from this guy to him is then just simply twice of x2. This distance here then would be x1, and then basically it's got to keep track of all the different distances, but nice and easy. So let me bring up the picture again so you know what all these different distances are. And of course it didn't show up on there. Excel's been acting really weird with not Excel, but PowerPoint. So give me 1 second. I'll tell you what all these distances are supposed to be. Okay, so in this case, you're told that this distance here is 1.5. Got all screwed again. And 2.2. Okay, so let's go back to my picture over here. So in this case, we're told is that this distance here is 1.5 meters, and the total distance across here is 2.2 meters. Good. So in this case, x2, as I have written down here, is 1.5 meters, and then x1 is going to be 2.2 minus 1.5. That's going to be that distance. So the total distance is simply the distance equal to x1 plus x2, which you can call some other distance d. So good. So this won't take too long, so I'll give you a few minutes to work on this, maybe 10 minutes or so, and then we'll start talking about other types of mirrors and other types of image formations from them. Keep you distracted from Cal 3.
Is it the third image from the front?
Yeah, the third image in the front, the one that's going to be right here. Yep. Yep. My Excel gets back here to my iPad. Or not Excel, Excel part 1. We had about 2 hours of sleep last night, so I'm gonna have problems with words today. Words will be my answer. That correct answer should be 7.4 meters. What's up?
Yeah, I think that's the answer.
That's right.
Right.
Okay.
It's
Right, so that's the distance for this guy.
Yeah.
Actually, no, this guy. So this is, let's see, what's 1.5? So 1.5 plus 2.2.
You're making a
Right, so that's the distance that this guy is away from this here. That's right. Okay. Which means that this image then is created at that distance. Okay. So that's good. So that's the distance of him. And then from there, would
that's why it's not. Okay, so you're getting out closer.
yes. So the first reflection is 1.5, and then from him, the second reflection of him is then, you're right, so 1.5 plus 2.2.
And then
Right, and then, so from there, you would have to add another 2.2 to that to put it back into the front here. And then that would then be the distance he is away on that side.
oh, I guess. I'm guessing I'm supposed to.
No, no, it's not.
Is it asking for how far those figures are on here?
Oh, that's a good point. How far from you?
Say it was
7.4, I think. Yeah. Meters. We did.
I guess 7.3.
Plus another 2.
Maybe that's where maybe I just confused myself because I just separated this and
Right, you can do it that way. Yeah.
it's basically just multiply each one as I found.
How many of them did you have? Right.
Right, but apparently I don't know.
No factors. What's up, Gavin? How'd it go? Yes.
Right, define this image here. So this one is only 0.7. So this one is only created by him, but ultimately we don't care about him because the third image here is created by this guy. Right. So if this is 0.7, then it has to be 0.7. Exactly. And then, so this guy then is going to be created by him. So it's going to be 1.5 plus 0.2 away from here. Now, the distance he is then away from this mirror now is going to be 3.7 plus 2.2. Means that this is going to be that distance. Okay, so that's going to be 3.7 divided by 2.5. This guy, second. But then this guy is this distance away from the mirror, but then he's an extra 1.5 meters away from you.
So that's where that's up.
A little. I
Okay.
confused myself.
Sure.
So you said it was from him, so.
Yes.
it'd be 1.5.
That's
So it's 1.5, and he's 0.7 times. Give me 2.2.
Oh, right, but we don't care about this guy. So we care about is this one here is going to create another image here. So that's going to be the third.
Oh, that's
Yes, the third one. So that's the third one in front of him. So this is the first one, the second one, and the third. So the first one then is right next to what you have. And then this guy then creates this guy. So this guy then is 1.5 meters here, but then he's 1.5 plus d away from this back mirror, which is creating this image. So that means this guy here is going to be 1.5 plus d away from this mirror. Not 0.7. No, 0.7 doesn't cover it out in this case. So d is the 2.2. 1.5 plus 2. Now, this guy then is going to create the third image out here. So now we have to figure out how far away he is from this mirror here, because this is creating the image from this mirror. So now he is out here. So here that's 1.5 plus 2.2, which is 1.7. So then he is 3.7 plus 2.2 away from here.
So that's then what, 5.9, right? So that means this image here is gonna be 5.9 meters away from this view. Plus the 1.5, you can say how far it is away from himself. Yes,
Okay,
okay,
thank you.
so that's 7.4. What's up? Good, okay, so this is, that's right. So now, we're not adding all these together.
Oh, we're not?
No.
Oh, yeah, okay, that's right.
Right, so all
Yeah, that
of
would
this
make
here
sense,
gives you to this one. right?
Yeah.
So
So you have to add the 1.5 here.
because that's how far he is away.
That's kind of paper, but
Yeah, we're not adding all those together. So this is just telling me where the first image is. This is just telling me where the second image is. And then this one is telling me where the third image is, which means the total distance the third image is away from him is this plus the one that's up,
okay.
which would then give me 7.4.
Why would you not?
Well, why would I, right? Because this is,
I thought you were like, so I thought,
so the 1.5 is only telling me the distance from here. And then adding the 2.2 tells me the distance from here. But this distance has to be the same as this distance. So that's then telling me this distance. And then that distance plus this distance tells me this distance right here. But then this guy has to then leave that equal distance on this side. So those distances are only telling me how far away is from here. I'm not simply summing them all together.
I thought that your reflection was this thing.
Well, we are looking for a little reflection. We want to know where the reflection is, not the sum of all those distances, right? So, and you can also think about it too as kind of like displacements, right? So in some cases, I'm going back the opposite direction. So if it's a displacement, I'm canceling out those distances. And again, so that tells me this distance, and then I just have to add on that 1.5 that tells me where this guy is. Got it? Okay.
Yeah,
Good.
I had to redraw my whole thing. So.
Okay. We don't got it. Okay. What's up? Because it's a plane mirror. So remember, plane mirror says that anytime I look at the plane mirror, let's say this is my plane mirror. When I see myself here or this pen, then whatever distance this is away from the plane mirror is the same distance it is behind. Okay. So what that means is, so for example, well, not 3 people and 3 people, but so let's think about what's creating what. Okay, so the guy here in this mirror is creating this image. This image then is creating this image, and then this image is creating this image. Right? So what I need to know then is, well, for this guy to create this image in this mirror, I need to know how far away this image is away from this here, because this is my new object. So what I know is that this guy here is x2 away, so that's 1.5 meters, which means that this distance is 1.5. But then this 1.5 meters is then total of 1.5 meters plus 2.2 meters away from this mirror, which is going to be this image. Okay. So that's what, 2.2, so that's 3.7. So that then is this distance 3.7 from here to here. So this distance from here to here must also be 3.7 because it's a 2. But now this image is going to create this image. This is the new object. So I need to know how far away this one is from this mirror here because it's making the image from this mirror. So this is 3.7 here. This is 3.7 plus 2.2, which is then 5.9. So you know this is 5.9 here, which means this also has 5.9. But I want to know how far it is away from here. So that's 5.9 here plus an extra 1.5. So it's a little bit. So it's just mostly keeping track of who made what. In this case, I never actually cared about this image here. So this image here, because they were not directly related to creating the third image. But if I wanted to know the fourth image, then I would have to know those two, because those two would be the ones that are making the fourth image.
Okay.
That kind of makes sense?
Yeah.
Okay. That's why I was trying to color code them up here, so you know which one is green. All right, everyone okay?
So good, that brings us to our next topic. So basically, we don't always just have plain mirrors, right? We have all kinds of different shapes of mirrors. So if you ever go into a fun house, right, where they got all the crazy mirrors, you can see all kinds of interesting images created inside of those mirrors from all of these different types of different mirrors, which are what we call curved mirrors. So in general, even though we have a whole bunch of types of curved mirrors, the most typical types of curved mirrors that we're going to find are actually what we call spherical mirrors. So we use these guys all the time. So spherical mirrors are probably the most popular type of curved mirrors, at least that's what we're going to pay attention to the most. Okay? So in general, we're going to be looking at, again, these spherical mirrors. In general, we have two types of spherical mirrors. Two types. The first type is what's known as a concave mirror, and the second type is what's known as a convex mirror. So what's a concave mirror? So a concave mirror is, look at the second part of that word, it says cave. So what that basically means is that it's a sphere, but you're going inside of the sphere. Like a cave, you go on the inside. So what that means then is your concave mirror is going to do something like this. Okay, so it's going to be a spherical mirror, which then has a constant radius of curvature. So this is my radius of curvature R. So R is equal to my radius of curvature. But in this case, my light is going inside. So in this case, I would have what's known as the principal axis. So this is what's called the principal axis. So the principal axis is the line that bisects the sphere. So in this case, it's going right through the center of the sphere. So it's equal on both sides. So it's completely symmetric. So in this case, what would happen then is I would send light in. So light then would be moving parallel to the principal axis in this case. And then what's it going to do? So in this case, it's going to continue to go. It's then going to hit the mirror. In this case, once it hits the mirror, we know it has to abide by the law of reflections, which means that here I would draw a 90-degree perpendicular here. So the angle of incidence would then be equal to the angle of reflection. So this line then would be curved down to do something like this. This one then would also do something very similar and curve down into this direction. This one then would do something similar, curve through into this direction. And then this one would hit here, and then again curve through and do something like this. Okay. So this is what we call a concave mirror. So concave mirror, in this case, all the light would enter inside of the mirror. What happens in this case then is that all the light rays would actually then be reflected through one particular point. So this one particular point here is what's known as the focal point. So in this case, all the light then is converged by reflections right through that particular point. Okay, so this is what we call a concave mirror. What's a convex mirror? So a convex mirror then is the complete opposite. So basically imagine that I take this thing and I flip it in the other direction. So now in this case, it's going to hit the back side of the sphere, which means for a convex, it's going to do something like this. Okay. So this is my convex. Again, I'm going to have my principal axis. So here's going to be my principal axis. I'm going to extend that in this direction. This is my principal axis. And what happens in this case? So again, we're going to do the same thing. So here I'm going to use a different color light. So let's say I'm going to use green in this case. So again, I'm going to send light parallel to the principal axis. And then what happens in this case? So this light's going to continue, and then it's going to diverge away. It's going to hit and bounce off in this direction. This one then is going to hit here and then diverge away, something like this. This one then is going to hit here and then again diverge, something like this-ish. Then this one is going to hit and again diverge away. It's going to diverge away in a line, say something like this. Okay? So in this case, what happens then is a convex causes the divergence of light rays. So basically meaning that if I have my eye out here, so this is my eye looking at these light rays, I'm going to see that these light rays are diverging. But again, my eye is something that's kind of stupid, and it wants to ray trace each one of these rays back to where it seems to have originated from, which means if I ray trace each one of these lines backwards, I actually do this properly, it turns out that all of these light rays appear to have originated at one particular point, where again, that one particular point is what's called the focal point. So good. So basically the concave causes convergence and then the convex causes divergence. Now, how do we then determine the focal points? Well, the focal point, it turns out, for spherical mirrors is actually directly equal to half of the radius of curvature. So we're not going to derive this, we're just going to state it. But for spherical mirrors, it turns out that the focal point, or what we call the focal length, so F here is what's called the focal length, which is the distance from the mirror to the focal point, is exactly equal to half of the radius of curvature. So it means here, this distance here then is my focal length, this distance then here is my focal length. So the distance from the backside of the mirror to the location of the focal point is what we call the focal length. Now, one thing to point out here, which is kind of important, or we're not going to make too big of a deal out of it, but I just want to talk about it. So let's say this portion here has kind of a thickness to it. It turns out that what we said here and here is actually only true as long as the thickness of this rays here is actually much, much less than that of the radius of curvature. So it turns out that this is actually only true if the thickness of the bundle, so T of the bundle of rays, is much, much less than a radius of curvature. So here, this is technically only true for a bundle of rays that satisfies this. Okay? Why is that? Well, that is what's known as what? Something which is called spherical aberration. So what ends up happening is if I took light rays that were far away from this, so let's say I'm sending in light rays that are coming up more up in here, happens in this case then is I'm going to reflect this guy through, but it's actually going to miss the focal point. And if I send a light ray then through here, bounce it off here, this one is also going to miss the focal point. So what happens is if the bundle of rays which is coming in this case what we call T is greater or at least closer to the radius of curvature, what happens then is that these light rays actually don't pass through the focal point anymore, it actually misses the focal point. This is what's known as spherical aberration. What that does is it ends up giving you a blurry image. It'll do things like elongate the image and then smears it so you can't actually see it. Now, where that becomes a problem are things like telescopes, right? So we want to use telescopes to be able to look at distant things like stars and planets and etc. But if I have a spherical mirror and the light rays are coming in close to the radius of curvature, it's going to smear out that object and I'm not going to really be able to see it. So the way to get around this is to go from using spherical mirrors to what's known as a parabolic mirror instead. So in that case, you're using more of a parabolic shape, which is that going to be flatter towards the outside as opposed to more curved as the spherical mirror. So in that case, you don't get the spherical aberration or get this kind of smearing of the actual image itself. Now, the problem with parabolic mirrors are they are very expensive to create, which means that instead of going to Walmart and spending like $50 or $100 on a mirror and a reflecting telescope, you're going to be spending thousands of dollars on a small little tiny telescope because it's a lot harder to engineer and create this particular parabolic mirror as opposed to something like a spherical mirror. So if you're ever buying a really cheap telescope or reflecting microscope or all these different things, it's going to be a spherical mirror. It's not going to be something that's parabolic. So you're going to get smearing, but you know, not a big deal. But so this is just something to kind of point out. Again, this is what's known as spherical aberration. Aberration. It's the light rays that don't pass through the focal point. Okay, this basically causes smearing of the image. Oops. Again, resolution of this. Parabolic mirrors. That's about as far as I'm going to go with that. Again, I just want to make sure that you know this thing actually occurs. There are ways to get around this, but we're not going to talk about parabolic mirrors or anything like that. So good. So next we want to start looking at is, right, so now we have these in general, two different types of mirrors. So we have the concave mirror, which causes convergence. We have the convex mirror, which causes divergence. So now we want to start investigating then is what types of image can I create by putting an object in front of one of these guys. So let's start looking at image formation. Image formation. Spherical mirrors. So I'm going to start off with concave. So let's look at concave first. So for concave, there's basically going to be three different cases. So let's talk about the three different cases. So look at case number one. So case number one, define what that's going to be. So here, first of all, is my concave mirror. Does something like this. Here is my principal axis. Here's my radius of curvature. Here is my focal point, which again is half of the radius of curvature. So case number one, what I'm going to do in this case then is I'm going to put my object somewhere out here. So in this case number one is going to be when what we're going to call the object distance is then greater than the radius of curvature. So this is case number one. So basically I just want it to be larger than the radius of curvature. So from here, I want to know, how do I actually then draw a ray diagram? So how do I actually determine the location of the image? So in general, we're going to do this by looking at three rays. These are what we call the principal rays. Now, typically when we draw a ray diagram, we only have to use two rays. You don't have to use all three, but I'm going to draw all three just so you know what each all three of them are. Okay? So let's talk about our principal rays. Principal ray number one is going to be the ray that goes parallel to the principal, hits the mirror, and then gets reflected down through the focal point. This is ray number one. So ray number one is going to go parallel to the principal, hit the mirror here, and then gets reflected down then through the focal points, and then continues on its merry way. That's ray number one. Ray number two then is going to be the ray that starts off here, goes through the focal point, hits the backside of the mirror, and then gets reflected parallel to the principal. So this is what we call ray number two. If I could draw a straight line out, actually. There we go. So that's ray number two. Finally, ray number three is going to be the ray that then goes and hits directly at the back point of the mirror, right where the principal axis actually hits it. In this case, so that means then is that this angle here has to be equal to the angle at which it is reflected off of, which means this one then is going to be reflected like this. Okay, so that this angle here is exactly equal to this angle here. Now, where these three rays line up, or at least where two of these line up, because all three of them will line up in the same particular spots, is the location at which the image is going to be formed. So in this case, my image will be here. This is my image. So basically pointing from the principal axis to the point where these three rays overlap with each other or converge to is what we call the image. So let's kind of see what's going on here. So here, in case number one, since the object is outside of the radius of curvature, what we can see here is here's my radius of curvature, here is my focal point. So we can see in this case then is that our image is actually created between the focal point and the radius of curvature. So from here we can see then is that S prime is going to be somewhere between the focal point and the radius of curvature. The other things we can see here is that this image is inverted, meaning that it is not upright. So in this case, it is in the opposite direction as the orientation of the actual image itself. So this is going to give us a inverted image. And the last part we can tell about this is actually going to give us a real image. We talked about yesterday what that actually means. Again, what a real image means as opposed to a virtual image is my reversible image on the plane mirror. If I put my piece of paper here on the back side, there was no light actually passing through the actual image itself. In this case, if I put this thing here, I would actually have image form on my piece of paper because the light is actually passing through the paper itself. So in this case, the light is coming in here, bouncing off, and then going through the image. So in this case, when I put my piece of paper, I'm going to see the object or the image of the object directly on the piece of paper. So this is what makes it a real image. So this is case number one. So case number one is anytime that the object is placed outside of the radius of curvature, the image itself is going to be somewhere between the focal point and the radius of curvature. It's going to be an inverted image, and it's going to be real. Okay? Case number two. Case number two, let's do the same thing. So here's my mirror. Here's my radius of curvature. Here's my focal point. And in this case, now what we want to do is take our object and put our object somewhere between the radius of curvature and the focal point. In this case, case number two, S is going to be somewhere between F and R. And so this is our object distance somewhere between these two. So again, here we're going to do the same thing. So we're going to draw principal ray number one. Again, principal ray number one is going to be the one that goes parallel to the principal. Hits then the mirror and then gets reflected through the focal point. This is ray number one. Ray number two, that green, I think, then comes through the focal point. It's then the mirror and then gets reflected parallel to the principal. Do something like this. And then finally, ray number three, again, is going to be the one that then hits the back of the mirror and then gets reflected off. And then it's going to do something like this. Again, if I drew this properly, what we should see in this case then is that what? Not quite properly, but close enough. We should see in this case then is that what? Our image is going to be created again where these guys actually overlap with each other. And we should find in this case then is that the location of our image is going to be somewhere outside of the radius of curvature. What we should find. So in this case, what we find is that S prime is going to be something bigger than the radius of curvature. Again, from here we can make responses about the image. So here again, we see that the image is inverted. And again, it is real. Because again, the actual light is passing through this guy. And we'll make some notes about what happens to this in just a second. Finally, case number three. Let's see, we'll do 3 and green. So case number 3. So in this case, again, here is my mirror. Circle. Here we go. Here's my principal. Here's my radius of curvature. Here is my focal point. Here is my object. So in this case, my object is going to be inside of the focal point. So green S will be less than the focal point. So less than the focal point. Good. What happens in this case? So in this case, again, what's going to happen is we're going to draw principal ray number 1. Principal ray number 1 is going to come, hit the mirror, and then again gets reflected through the focal point. So it's going to come down something like this. In this case, drawing ray number 2 is kind of awkward because the focal point is beyond it, which means it's kind of weird to draw it to go through it and then still hit the mirror. So in this case, we're only going to draw principal ray number 3, which means principal ray number 3 is going to send this guy down to here, reflect off of here, and this is now going to do something like this. Now here, what's basically happening is, again, my eye is out here. But what my eye is seeing, again, is that this right here and this right here are diverging away from each other, which means that my eye wants to ray trace those guys backwards to where they seem to have originated. So I'm going to ray trace this guy backwards here, ray trace this guy backwards here, and where these ray trace lines converge is then going to be the location of my image. So in this case, my image is going to be here. This is my image. In this case, what we can see then is that what my image location will actually be negative. Negative in the fact that what it's now going to be on the back side of the mirror. Again, we can make some notes about this. What happens in this case then is that this is now an upright image, meaning that the orientation of the image is exactly the same orientation as the object itself, so it's upright. But this is now a virtual image. And it's virtual because, again, if I take my piece of paper and I put it directly here at the place that the image is supposed to be formed, what I can see in this case then is the light is coming in this direction, bounces off and moves in this direction, so no light actually makes it back behind the mirror, so this is a virtual image since no light actually passes through. Okay? Make a few more notes. So what happens here is that what's actually going to happen is the further that this object is away from the radius of curvature, the closer then this image is going to be formed to the focal point. But then as I start moving in towards the radius of curvature, what will happen then is that this image here will start to be pushed also towards the radius of curvature. Okay. Until eventually this thing then passes through here. And as it passes through, in this case, what happens then is once I pass through here and I start getting closer to the focal point, the further that this image will then be created. Okay. So the closer I get to the focal point inside of here, the further the image then will be created away from the mirror itself. Until eventually, I get inside of the focal point, and then in this case, as we can see from here, it then just becomes simply a virtual image. But the closer and closer I get to the back of the mirror, the closer that the image gets to the mirror itself, and the smaller it becomes. The closer I get to the focal point, the farther away it goes, and the bigger it becomes. So just some random notes to add on to these things. Okay? So this is concave. Let's do one example then of convex. So now let's look at convex. So for convex mirrors, we're gonna do basically the same thing. So here's my convex mirror. Here is my principal axis. Now in this case, the radius of curvature is over here, which means that the focal point is over here. So in this case, there's only one case. I don't have multiple cases. Because in this case, I can't put it inside of the focal points or anything over on here because that's not where the light is. The light is over on this side, so we just don't have to worry about it. So in this case, there's only one case. So here's my one case. Here is my object. So again, let's figure out how to actually draw ray diagrams. So here again, principal ray number 1 is going to go parallel to the principal. In this case, it wants to, pardon me, get reflected through the focal point, but it can't because it can't pass through the actual mirror itself. So what's going to happen then is it's going to be reflected away from the focal point. So this is actually going to be ray number 1. Ray number 2 then, again, is going to be the one that wants to go through the focal point on this side, but it can't. So it wants to continue through here, but it can't, which means it's actually going to be reflected back parallel to the principal. So it's going to be ray number 2. Again, this one wants to come from here, and it gets reflected off this way as if it came from the focal point. This one wants to go through the focal point, but by the time it hits the mirror, it then gets reflected back parallel to the principal. Now, again, my eye, which is sitting out here, looking at what's actually happening, again, sees this line here and this line here diverging away from each other, so wants to ray trace these guys backwards and see where they actually came from. So in this case, it's going to ray trace this one backwards to the focal point. Pardon me. Simultaneously, it's going to ray trace this one back parallel to the principal. And then where these two ray trace lines cross each other, this is where the image is formed. So this is my image. So in this case, my image formation then is going to be again upright. And it's going to be vertical. Now, one thing to note about this one is the closer that this object becomes to the mirror itself, the closer then the image will also go to the mirror and the larger it's going to become. So the further it is away, the closer it's gonna be to the focal point, and the smaller it's gonna become. So the closer it gets to the mirror itself, the closer that the image will become to the mirror, and the bigger it's going to be. It was okay? So these are the ray diagrams for each one of these. This is how we would actually draw them. This is something I would expect you to do on the exam itself. But now we have to ask the question, okay, so if anytime I give you an object with an image and etc., and I ask you to find the image location, am I going to make you draw this thing every time? Yes, but am I going to make you do that to figure out where it is? The answer is no. So we want to mathematically determine how do we actually do this. And the way we would do that is we would simply draw one of these pictures here, such as the first one, and we would do a whole bunch of geometry. From that geometry, we can then gain a simple expression. We're not going to do the geometry. I'm not going to derive this for you, but the result of all this is what's known as the mirror equation. So what does a mirror equation say? The mirror equation says that 1 over the object distance plus 1 over the image distance is then equal to 1 over the focal length. This is what's called the mirror equation. Now you know this from lab as the lens equation. That's because this works for lenses too. And we're going to get there later, which is nice because it works for 2 different scenarios. Life is great. We also have what's known as the magnification. Where the magnification then is the size of the object. So we have the magnification then, which is equal to the image height divided by the object height, which is then equal to negative of the image distance divided by the object distance. So this is what's called the magnification. So this is how big is the image relative to the object. Not too bad. That's it. So let's do a quick example. Then we'll do another example tomorrow. Well, not tomorrow. We're not gonna be here tomorrow. At least I won't be here. So this says we have a 1.5 centimeter tall ring is placed 20 centimeters from a concave mirror with a radius of curvature of 30 centimeters. Wants us then to determine the position and the image and its size. So let's go ahead and do that. And then after that, I'll do that on Monday. We'll write down some sign conventions for these things, but let's do this now. So here's our example. So basically what's happening here is we have a concave mirror. So here's my concave mirror. Great. We know the radius of curvature is equal to 30 centimeters, which we know that our focal length, which is equal to half of our radius of curvature, then must be equal to 15 centimeters. So that means that what? In this case, here's my radius of curvature. Here then is my focal length. And then we're told we put a ring in front of that, where that ring is 20 centimeters. So it's going to be closer to the focal point. And we're told the height of it, where the height of the ring was how much? 1.5 centimeters. So from here, we want to know is A, what is the image distance? So where's this guy created? And then part B, what is the image height? So these are the 2 things that we want to know. Now, this satisfies, of course, case number 2. So case number 2, we already know that this guy's going to be created out here somewhere, but let's go ahead and draw our ray diagram just for some practice. So again, a ray diagram says that we draw our parallel principal ray number 1, parallel to the principal axis. And then it's going to be reflected down through the focal points. Ray number 2 then is going to go through the focal point to the mirror, and then gets reflected back parallel to the principal, and then our image is going to be somewhere out here. So our expectation then is that our image distance here should then be greater than the radius of curvature. And the magnification should be larger, so I should see it bigger based off of my diagram. Well, let's go ahead and do that. So A then says 1 over the object distance plus 1 over the image distance then is equal to 1 over the focal length. In this case, we know the object distance, we know the focal length. So I can then say 1 over the image distance is equal to 1 over the focal length minus then 1 over the object distance. From here, I can find a common denominator, which is just the product of the 2. So I'm going to get then that what? The object distance minus the focal length divided by the object distance times the focal length. Finally, inverting this then gives me the image distance then is going to be the object distance of the focal length divided by the object distance minus the focal length. This is gonna be my image distance. Good. Again, in this case, we know our object distance is what, 20 centimeters. So let's plug all those things in. So we get our image distance then is gonna be 20 centimeters times 15 centimeters divided by 20 centimeters minus 15 centimeters. Overall, this is gonna have units of centimeters. So this is gonna be what, 20 times 15 divided by 5, which is the same thing then as what, 4 times 15, which is the same thing as 45 centimeters. So what this says then is that the image is created 45 centimeters away from the mirror, which we know is bigger than, what I do?
It's 66.
Oh, is it 60? Can I not multiply? Oh yeah, it is 60, isn't it? I was saying no 3 times. Go. Thanks, Kevin. 60, but anyways, it's bigger than the radius of curvature, which is what we know. Because again, radius of curvature is. So let's look at the sides. For the sides, what we know is that the magnification for part B is then equal to the image height divided by the object heights, which means then that our image heights, which is then also equal to negative of the image distance divided by the object distance. So from here, what this tells me then is that my image height is then equal to the magnification times the object height. But again, the magnification is then simply equal to negative s prime over s. So let's do that. So this becomes a negative s prime over s times h. Do that in the other slide. So then again, h prime then is equal to negative of s prime, which was 60, divided by s, which was 20, all times h, which was 1.5 centimeters. So that's then negative 3 times 1.5 centimeters, which then works out to be negative 4.5 centimeters. I multiply that one, right? We're good. Okay. 2 hours of sleep. So as we see, it is inverted. That's what the negative sign here means. And it is bigger because it's been multiplied by 3 times. So it has to be bigger just like our picture. So Monday, we'll talk about sign conventions. So make sure we get all our sign conventions, make sure this thing works in all possible scenarios. And then we'll do another example. And then we'll move on. Question, we should be done. When we keep going at the rate we're going at now, we should be done by like Tuesday. Which means for Wednesday and Thursday and Friday, we have options. So we could go back and do AC circuits. Or maybe.
Let's just review.
Yeah.
We'll see. If it was gonna be AC, it's gonna be something very small. So AC is kind of difficult, but we can't ask very much questions for it. So, well, we could do AC for like 2 days and then review on Friday.